So, hello to everyone who's watching the session on YouTube. We'll wait for like 5-10 minutes so that a few people can join the session in person. So, if no one join, let's say like 5-10 minutes, then I'll just get started with discussing. So, yeah, we'll get started with the session in like 10 minutes. Okay, so it seems that no one has joined the session in person yet. So nonetheless, we'll just get started. So first of all, just to introduce myself to everyone who's watching on YouTube. So hello everyone. I'm Lakshay Saki, the problem-solving TA for NPTEL Social Network Analysis course for the Monday 6 to 8 p.m. sessions. And I believe this will be our ninth session. Uh, like so sorry, I don't think we had a session last week. That was because I was really unwell, so we did not really have any eighth session. But technically, this will be a ninth session because we'll be covering topics related to week 9 this week, and we'll probably have a makeup session for the previous week at some point in the future. So yeah, definitely we'll let you know whenever that the makeup session will be. But yeah, for now, uh, as for today's session, we'll be discussing basically first we always do the summary of the lectures uh, which were or the topics which were discussed in this week's lectures, the ninth week, and then we'll be in the end going over some of the problems related to the lecture contents which can help you solve the quiz for this week. So I guess since no one is in the session yet, although I would have loved some people to be physically present in the session, but nonetheless, I guess we can get started. I I have like always I have a doc prepared with me, so I'll just share my screen and share that document with all of you guys. So yeah, uh, just let me share my screen. Okay, so I hope my screen is visible to everyone. So yeah, so this will be the ninth. So as I said, this will be this is the ninth week, and so we'll be covering the topics covered in 90s lectures. So once again, usually what's usually the pattern, I have first prepared some you can treat these as notes of this week's lecture slides, like the important topics which are covered in this week's lectures, and then so first we'll be in the first half of the session, maybe I don't know uh, some more than half of session will be spent on revising these notes and everything, and then we have a bunch of questions, only 7 questions for today, which are I believe somewhat simple questions, like if you uh, if you are able to follow what's discussed in these notes, which is also I don't think too difficult, but it's more like just a bunch of information being thrown around. So I'll try to organize that information for you guys, and yeah, hopefully after that this won't be uh, too difficult, really. Yeah. So the questions won't be too difficult. So yeah. So I guess we can now get started. This week, actually, we started, and actually in the lectures there was a new topic started, which was about anomaly detection in social networks. And so, first of all, how do we motivate this problem? Like, what do we even mean by anomaly detection, and why is it even necessary? So, first of all, note that these days, uh, there's a lot of data available in the world. A lot of people are collecting data about different kinds of stuff, and so there's a lot of data available, but we are still starving for knowledge. Although we have a lot of data, still compared to the amount of data, we still don't know what to do with so much data, or how to optimally process all of this data. And because of this, or maybe because we are not able to process this data efficiently, it's natural that some data which we gather will be anomalous. Like there will always be some uh, bad entities during our data collection process, which will try to ruin this data for us. And so some anomalies, or these are called anomalies, and so some anomalous events occur in relatively infrequently in these data. And then it's really important, because we want to actually process this data for further uses, say machine learning, deep learning, or whatever you want to use this data for. then we really don't want our models or anything to learn things based on this anomalous data. We want to realize that this data is bad, and we want to rule out all of this data. Yeah, but note that classifying what data point is anomalous and what is non-anomalous is somewhat difficult, because these anomalous events occur relatively infrequently, and when they do occur, their consequences can be quite dramatic, and uh, uh, dramatic in a negative sense. So they can really harm us, although these occur very infrequently. So let's say, like, even if they occur like 0.01% of times, then it's really difficult to detect something which is like, so basically we have to build a classifier which which classifies this 0.01% of things correctly, and the remaining 99.99% of things also correctly, which is somewhat of a non-trivial task. And this is really important because the consequences of a bad classification are can be quite bad for us. So yeah, so maybe just revising what is an anomaly. So anomaly is a pattern in the data that does not conform to the expected behavior. And this is also usually referred to as outliers, exceptions, peculiarities, surprises, and so on. Although there is a bit of a difference between like graph anomaly and outliers, but we'll come to that later on. But on a very high level, you can refer to anomalies as outliers, exceptions, and so on. And the branch of data mining concerned with discovering rare occurrences in data sets is called anomaly detection, because indeed we want to detect these anomalies and somehow like try to prevent them from entering into our data processing stage. And this problem domain has, like Eric already said, like the data is used usually these days in a number of things. So obviously, this anomaly detection is also useful in a number of things. So yeah. So what's the basic difference between outliers and graph anomalies? So although these are like quite similar, like I said, like anomalies can also be referred to as graphs, but uh, somewhat of a very like basic difference between outliers and graph anomalies is okay, like so usually if you are given a bunch of data points, uh, then you say that some data point is probably an outlier because that data point does not maybe that data point is a bad point, or like that data point does not conform to the to all of the data points or something. But what's a graph anomaly? Note that graph anomaly does not need to be just a data point. As we already said, like anomaly is a pattern in the data. So note that outliers, usually when we refer to outliers, we mean that some data points are bad, like that some data points do not conform to the expected behavior. Whereas in graph anomalies, what we are actually saying is, okay, like when we are building a graph, maybe out of when we are building a graph or a social network or something, so there is some kind of a pattern. It's not an individual data point which is an outlier, but some kind of a pattern or some kind of intermixing, it's some kind of interaction going on between some points, and this whole interaction is suspicious, and that's what is called graph anomaly. Like so that's like so graph anomaly does not just refer to one single point. So outliers are also like graph anomalies, but this graph anomaly is a more general term because it can capture like because it captures suspicious interactions between a multitude of points together also. It's like some suspicious pattern in the data. So that's why like graph anomalies are much broader term than these outliers. So this is so graph anomaly detection is a much harder problem than outlier detection. Yeah. So like I already said that graph anomalies may exhibit interdependencies, whereas like when you're referring to outliers, you usually refer to those individual data points as being outlier or not. So yeah, and yeah. So what are the challenges or and consequently the opportunities um, in this graph anomaly detection problem? So note that the very inherent idea of a problem having some kind of an anomaly is an ill-defined problem. Like you cannot have some unique definition for the problem of graph anomaly detection. One might say that some certain phenomena is an anomaly. Some other person with some other use case might refer to some other phenomena as an anomaly. So this really depends on the context. Like, it's not really fixed, like what is an anomaly and what is not. And the definition becomes meaningful only under a given context or an application. But nonetheless, even though it's a very ill-defined problem and this is like very problem specific, still we'll try to have some kinds of generalizations as best as we can. So first of all, like taking inspiration from the definition of outliers according to Hawkins. So outlier is an observation that differs so much from other observations as to arouse suspicion that it was generated by a different mechanism. So this is the definition of an outlier according to Hawkins. But not like so. Taking inspiration from this, maybe we can say that okay, graph anomaly is maybe a pattern that differs so much from other patterns as to arouse suspicion that it was generated by a different mechanism. So yeah, just a high level idea. So we try to define this general graph anomaly detection problem. So suppose we are given a plain attributed static / dynamic graph database. So whatever you want it to be. And what do we want to find? The graph objects that are rare and that differ significantly from the majority of reference objects in the graph. So basically, the graph objects which displays different characteristics from the majority objects in the graph. And a graph object is flagged as anomalous if its rarity score exceeds some certain user-defined threshold or something. And like how it can be defined anomalous, as we already said. So a graph point is anomalous if it is rare, if it is isolated, if it is surprising, or it needs too many bits to describe under minimum description. So this last part just need too many bits to describe under minimum description length principle. So this is something you probably won't be, so you guys probably won't be able to follow right now. And yeah, this is, I don't think this is anyways covered in the lectures because this is more of an information theoretic thing. And yeah, I don't think they're covering any information theory. So you can you don't need to think about the fourth point too much, but I hope like the first 3 points are uh, clear by themselves. So first of all, so there's this problem of the graph anomaly detection problem being ill-defined. Then another challenge for us is that this problem really is very, very data specific. It's not like one glove fits all. Like we already said, the context of data as well as context of problem is very important in defining what is a graph anomaly and what is not. So the scale of data is a very big challenge because the larger the amount of data, the harder is anomaly detection in that data. Because then it's like finding a needle in a haystack. Yeah. And then there can be certain complexity in the data like user demographics, interest, roles, as well as different kinds of relations between different data points. And you need to consider all of them before describing that one kind of pattern is a anomaly and not just something resulting from user demographics or something. So yeah. And more importantly, rather than other than these data specific challenges, as I said, there are these problem specific challenges also in graph anomaly detection. And for example, one of the major challenges in the problems is lack of labels and noise of labels. Uh, for example, if there is some problem and yeah, so suppose for any problem, if you want to see how your graph detection algorithm is performing or something, first of all you need some kind of test data to test it on, how is my algorithm performing. And for testing you already need to know whether the data actually was anomalous or was it not anomalous. So you need some kind of label data first of all, and this for the for detecting graph anomalies for certain problems. But note that even like finding this label data is a major challenge. For example, human like so this is a quote by Kahneman that humans are encouragedly inconsistent in making summary judgments of complex information. So suppose if you want to label a review as fake or not, uh, then first of all you need some label data for this problem. But who is going to label that data? That should be done by humans, right? Because humans are the ones who have to label the data. But it's observed that humans can perform just as good as random in labeling a review as fake or not. So if even humans are not able to explicitly specify like what should be the correct label of the data, then our algorithm does not even have a starting point to base on. Like what is even the objective of the algorithm if we humans even don't know the correct answer to the problem. And that's why like supervised learning or like supervisor methods are less attractive in these kinds of problems. But still, there are some kinds of like heuristics or some kinds of algorithms which can overcome some of these problems, as we'll discuss later on uh, as we go on. And so another problem in like this graph anomaly detection is class imbalance. That anomalies are very rare. As I already said, it's like finding a needle in a haystack. So it's like 99.99% of cases will be good and only 0.01% will be bad. But then you want to really identify the 0.01%. And that's like really like normal classification algorithms will fail in these kinds of cases because like here there's the imbalance is too large. And then there are like the asymmetric cost of error. This is also a major challenge. That cost, so cost of mislabeling a good data instance versus bad instance may change on the application. Like so, there are two kinds of mistakes which your algorithm can make, right? Your algorithm can either label a good data as bad or label a bad data as good. And note that these two things do not carry the same penalty in all contexts. For example, like, and it depends on the application. For example, mislabeling a cancer patient as healthy could cause fatal consequences, but like mislabeling a healthy patient as cancerous may not cause too much of consequences because the person can just get checked out again and he'll realize that he's healthy, he or she is healthy, and then everything will be fine. So, but similarly, like mislabeling an honest customer as a fraudster could cause loss of customer. But mislabeling, but note that here, like mislabeling a fraudster as a honest customer may also be may also cause some issues, but still, like at least in India, like what we usually believe is that uh, an innocent should never be charged as guilty, even if it means some guilty are charged as innocent. So yeah, so that's the idea here. So that's why like there is a asymmetric cost of error attached to this kind of a problem. And then moving on, like some further problem specific challenges are like so the anomalous behavior can change dramatically over time. Okay, so suppose you have some algorithm which can detect the anomalies uh, to a reasonably good uh, in a reasonably good manner. Uh, but note that like this your algorithm, even though it's working now, but over time, let's say like 2 years from now, your algorithm may not work anymore because like these anomalies are like with these bad elements who are causing these anomalies can realize that your algorithm is doing some kind of this, and like these adversarial elements can like change their anomalous behavior so that your algorithm does not work on it anymore. So one has to keep updating his or her this graph anomaly detection algorithm also, because anomalies can also change over time. So an algorithm should also change over time. And obviously, another challenge is this. explaining away the anomalies. Like, okay, one can mark something as being anomalous or not, but so this is one problem. But then giving a reason or like justifying why was some X thing marked as anomalous, whereas some Y thing was not marked as anomalous. So classification is like we realize that classification in this anomaly detection is already a difficult problem, and then justifying this classification is an even more difficult problem, because usually you will have some kind of very complicated mathematical models under the rugs which would be classifying something as anomalous or not, but then justifying these models which are just crunching numbers in the backend is really something which is kind of hard for us. So yeah, so this explaining away the anomalies is also definitely a very very big challenge. Okay, so moving on, maybe so after we realize that there are some kinds of challenges in anomaly detection and all, then maybe we can move on to try some like try some heuristics or see what kind of methods can detect like anomalies up to a certain extent, even though as we discussed that the challenges being of problem specific challenges or data specific challenges, the problem being ill-defined or so on, but still challenges does not mean that we stop working on this problem altogether, right? It means that we have more opportunities to try and work around these challenges or overcome these challenges. So yeah, so maybe let's start with this. So anomaly detection. Let's start with this anomaly detection in static graph. So static graphs are the graphs which do not change over time. So we'll also come to dynamic graphs, which are graphs which change over time. But for now, we'll assume that the graph is not changing over time. So the problem is that if we are given the snapshot of a plain or attributed graph database, then we have to find the nodes or edges that are few and different or deviate significantly from the patterns observed in the graph, right? And then static graphs can be of two types: plain graphs or attributed graphs. So plain graphs such as normal graph, which have vertices and edges, and then attributed graphs are graphs where maybe these vertices and edges also have some kinds of attributes attached to them. But usually the vertices have attributes attached to them. So yeah. And then so usually in static graphs, if one has to detect this these n graph anomalies, then there are some uh, methods which people use. So some of the methods utilize the structure of the graph, like what are the different structural properties of the graph, and using those properties, people try to classify something as anomalous or non-anomalous behavior. And then there are uh, two kinds of structure-based approaches in static graphs usually. So one is feature-based approach, where we try to exploit the graph structure to extract graph-centric features, such as maybe graph-centric features are features like node degree or subgraph centrality and so on. Whereas there's another kind of method which is proximity-based approaches, and in these proximity-based approaches, we try to use the graph structure to quantify closeness of nodes in the graph to identify associations. So here we are using graph-centric features in the feature-based approach, but here we are trying to quantify how close are two nodes to each other. And this closeness is not just with respect to the distance of the node. This closeness again can depend on the problem at hand. With respect to what thing are we saying that the nodes are close? Maybe with respect to the neighbors of the nodes are similar, maybe the shortest distance is small, maybe the nodes are have a lot of shortest path between them, or centrality is high or something. So we try to form associations between nodes in proximity based approaches, whereas in feature based approaches we try to extract these graph centric features and base our decision on anomaly detection with this. So yeah. And then there are a number of like feature-based approaches. So I don't think we go into all of these in the lectures, but like just a high-level flowchart. So there are many features which are used in different networks, and this is also note that not an exhaustive list. So there are node-level features like eigenvector, closeness, betweenness, and so on. Similarly, there are dyadic features. Then there is this ego net, then a node group, global features, and so on. So there can be multiple kinds of things. So this is just a high-level overview of some graph-based features which are there. And moving on, like giving like some examples of feature-based approaches. So one of the approaches which were discussed in the lectures was this oddball approach. And what it does is it extracts EgoNet-based features. And note that what's EgoNet. So this is something which has been discussed in the previous lectures also and in one of the previous sessions, but I'll just reiterate for everyone to follow. So EgoNet is nothing but you define an EgoNet with respect to some node of the graph. And the EgoNet with respect to, let's say, the node V will be the vertex V along with the neighbors of V and the induced subgraph on these vertices. So the only vertices which you consider are the vertex V and all the neighbors of V. And then you consider the edges of the graph as the edges in the induced subgraph of these many nodes. And that's what you call EgoNet with respect to the vertex V. So in this oddball feature-based approach, we use this EgoNet-based features. So so we try to find pattern that most of the EgoNets of the graph follow with respect to the features. And like what's an EgoNet? So is the definition. Like EgoNet is the induced one-step subgraph for each node. And like, this is just like what I just said. And this has been discussed in the lectures before and also. And then the question is like, okay, so we are saying that find patterns that most of the EgoNets of the graph follow with respect to those features. And like we are saying that we first extract the EgoNet-based feature. So what features are we extracting? So this is a important question, like what features should we use to characterize a neighborhood? So again, the features can be like really problem dependent, but some features like which are very universal or like almost always used in these oddball based approaches, we'll be discussing them. But note that this is again not an exhaustive list of features. You can produce features with respect to your problem statement. Yeah. And then the second problem is like, first of all, what features do we want to use? And the second thing is, what do we define? So even when defining this feature, how do we say like which feature is normal and what is not normal? So what's the threshold on something being normal and something not being normal? Again, it's a very subjective and problem specific question. So note that like there are levels to the complicatedness of this problem. So it's not really a very straightforward problem. But still, like, so some features which are used in these oddball based approaches are like these near cliques and stars. So those nodes, so what are near cliques and stars? So those nodes whose neighbors are very well connected, which are also called near cliques, or the nodes which are like not at all connected, which are also called stars, usually turn out to be strange. So if you look at these nodes, so if you look at EgoNet of any node and you find that EgoNet is almost a clique or is almost just a star, then probably like that EgoNet will be anomalous. Because in real world networks, like usually it's not observed that you get these cliques or uh, these stars. The second kind of feature which is usually prominent in these approaches are these heavy vicinities. So if a person I has contacted n distinct people, we would expect that the number of phone calls would be a function of n. And note that extreme total weight for a given number of contacts would be suspicious. So, for example, faulty equipment that forces redialing. So, yeah. Uh, so, like some nodes having very high vicinities uh, will be also possibly a cause of like anomalous behavior. So, and similarly, like dominant heavy links are like a very heavy single link in the one step neighborhood is also suspicious. indicating maybe a person is like keeping on dialing or not. So this is just an example, but usually like it's observed that dominant heavy links are also usually some kind of anomalous behaviors. And these are just like maybe diagrammatical interpretations of all of these things. So for example, with respect to this node, we have like with respect to this egonet, we have a like near star kind of pattern that these nodes are very not very well connected. So that's the anomalous behavior. Similarly, here around this node, all the nodes are very well connected. So that's a near cleave. So this is also an anomalous feature. Similarly, this is heavy. Uh, so note that this is like this is like an example of a heavy vicinity node because like even though you're making small number of phone calls, but the total number of phone calls is like very large. So this is heavy vicinity, and similarly, this is an example of a dominant heavy link. So what features should we usually use to characterize a neighborhood? So as we said, like these are some of the these are some things which one can always use, and like if these are observed, then usually this is a classic case of like this this ego net being anomalous. And trying to quantify these things more mathematically, not just these things, but so we usually discuss that real world so networks usually follow some kind of power laws. So we can drop some power laws for these ego networks. So on a very high level, we can drop some, or we can like using observations, we can drop some kind of power laws for these different ego nets of real world networks. And if some ego net does not follow this kind, the power law which we have at hand, then probably that egonet is an anomalous egonet. So yeah, so these power laws are also so usually like real world networks follow these power laws, and if let's say some subgraph or some part of it is not following some power law which we define, then you can think that okay, maybe that subgraph has some anomaly and that's why it's not following a power law. So for example, like what features should we use to characterize a neighborhood? So suppose if you have like ni as the degree of node I, you know. So okay, so no, Ni is like number of. So for a specific node V, we are looking at the ego network of V, and Ni is the number of neighbors of V with degree I, and then Ei is number of edges in ego net I. Okay, okay, sorry. So suppose I is okay. So I think I have like confused you guys. So sorry, like let's just start again. So Ni is just like the degree of node I. So suppose I is the node which is given to us, then Ni is just the degree of node I, and Ei is just number of edges in the ego net of I, and then Wi is the total weight of ego net I, and this lambda Wi is the principal eigenvalue of the weighted adjacency matrix of ego net I, and it's usually observed in real world networks that uh, mm, there are some kinds of power laws which can detect these kinds of issues, these kinds of anomalies in the network. So if you draw up a E versus N graph, then it can detect near cliques and stars. If you draw a W versus E graph, then it detects heavy vicinity. And if you draw a lambda versus W graph, then it detects a single dominating heavy edges. So yeah, and usually like for these graphs, so how do you say like how do you take these? So usually for these kinds of graphs, it's usually observed in real world that these graphs follow some kinds of power laws, and if your network is again not following these power laws, then uh, there is some kind of anomaly going on. So for example here like there can be some kind of power law for ego net density. So this is in E versus N graph, there is like EI is like proportional to Ni to the power alpha, where alpha is between 1 and 2. And if this is not followed, then probably it's an anomalous behavior. Similarly, in this W versus E graph, again, it's observed usually that Wi is proportional to Ei to the power beta, where beta is greater than or equal to. If this kind of law is not followed, then again you can say maybe there's this heavy vicinity anomaly. And similarly, yeah, in this lambda versus W power law, if lambda is proportional to W to the power gamma, where gamma is usually between 0.5 and 1. And again, if this power law is not followed, then you can say that there is a dominant pair kind of anomaly present in the equilibrium. So yeah. So note that these three kinds of graphs and their associated power laws helps us detect these anomalies in the equilibriums. So yeah, and this is like a very high level. I know that all everywhere we are just using these power laws and the egonets and all. So we are just utilizing the graph structure, and that's why it's a structure-based method. And the features which we are using, since we are using different features, hence this is a feature-based approach. And the name of the approach is this odd. So yeah. So I hope this is clear to everyone. Then maybe we can move on. Like, so there are some other methods like for anomaly detection in static graphs. For example, like you have these community-based methods, uh, which rely on finding densely connected groups of close by nodes in the graph. So so we already know what a community is, right? We have discussed community multiple times in previous sessions. So then we know like what is a community, and then we can spot edges or nodes maybe that have connections across communities and which are like kind of bridges. So note that one can think that okay, maybe like if some nodes do not belong to any community, they are, and these nodes will be far and few between, like as we already have said like before also, but most of the uh, edges and nodes of the network lie in one community or the other. So bulk of the network is in lies in some communities, and then the nodes which do not lie in any community, or like the edges which do not lie in any community, like are differing from rest of the network. So they can also probably be termed as anomalous. Although not always, but in certain contexts, this can certainly be anomalous for us. So yeah, and this can be just thought of as finding bridges. So this can just be thought of as finding bridges or bridge nodes or edges that do not directly belong to one particular code. So yeah. And then in static graphs, there are some further examples of community-based approaches. Like several real-world data can be represented with bipartite graphs, where the bridge nodes reveal interesting phenomena. For example, so this is just an example from some real-world network that in publication networks, authors versus unusual papers written by authors can be revealed using these bridge nodes. Similarly, in P2P networks, users versus cross-border files also can be done using these bridge nodes, similar in financial trading networks and customer product networks. Okay, but again, like okay, so now we are circling back to what we had to the question at hand, which we had like some few weeks ago, like how to find the community of a given node, which is also referred to as neighborhood of a node. And this is similar to the problem of like community detection or like community classification of a node. And then the second problem is how to quantify the level of the given node to a rich node, right? So one answer maybe to how to find community of a given node is like so some of the approaches we are already discussed in community detection and all, but maybe another thing this was also discussed actually previously. Like one can use random walk with restart page, personalized page rank scores of all the nodes. Then nodes with high page personalized page rank score constitute the neighborhood of a node. So these kinds of approach we already have discussed, but like just it can serve as a quick revision or like yeah, this is one of the methods using which we can detect communities and hence detect anomalies, and maybe how to quantify the level of the given. So this is not the only way by which you can implement community-based method for anomaly detection in static graphs. This is one example. There can be further examples, and yeah, you can apply any of the community detection-based approach which we discussed previously, and you can think of it as a community-based approach for like graph anomaly detection. So this is just one of those approaches. And how to quantify level of the given node to be a bridge node. So the pairwise personalized page and scores among all neighbors of the given node are segregated. So basically, like you can use, so the high level idea is you can use those PPR scores to quantify levels of a given node to be a bridge node. Because note that a node with a high PPR score means that that node is very essential to the node with respect to which we are doing this random walk thing to compute based on. And so maybe that node has a higher tendency to be a bridge or something. So this is just like on a high level doing of that one. And then so there are like other approaches also. So like Chakravarti in 2004, so this approach is called like AutoPart. This is also a community-based method where they say that nodes with similar neighbors are clustered together. And anomalies are usually the edges that do not belong to any community, and nodes that have many cross connections to multiple different communities are considered to not belong to any particular cluster. And yeah, so without going into like details of this autopart algorithm, I don't think we went into details in the lectures either. So autopart is a parameter-free iterative algorithm based on the minimum description and principle. And note that like since we have not discussed what is minimum description and principle because it has its roots in information theory and that's like really out of the scope of this course. So like we do not discuss like what this autopart is actually doing. But on a high level, like anomaly detection here also works similarly, and this is also a community-based method for anomaly detection. Okay, so I hope it makes sense. So I'll just mute myself for 2 minutes because I need to get some water and then I'll be. So I'll just mute myself for 2 minutes. Hi. Sorry for the break, guys. So coming to yeah, so here we discuss these community-based approaches for static graphs, and right now we are just talking about simple graphs, not about attributed graphs. So the next thing is again we should talk about the static attributed graphs and like maybe structure-based approaches in these graphs. So note that attributed graphs are like just like normal graphs, but maybe like the nodes or edges are associated with some different graph attributes also. And so like while detecting or like while classifying something as an anomaly or not, you have to take these attributes into account also, other than just the structure of the graph. So usually the high level idea in the structure based approaches for the static attributed graphs is like identifying substructures in the graph that are structurally uh, connectivity wise also, but attribute wise also. You cannot just say something is an anomaly just based on the structure in this case. You also have to take into account the attributes associated, right? So here, so as you can see, like this a bit harder problem than like anomaly detection in the non-attribute graphs, because here you have another thing which can vary, which are these attributes. So the first problem here is like finding unusual substructures in a given graph, and the second problem is finding unusual subgraphs in which nodes and edges contain like non-unique attributes. So yeah, something like that. And so some high-level ideas for what one can do. Maybe we won't go into too much depth in these static attributed graphs, but some higher idea of what you can do in structure-based approaches is maybe looking for structures that occur infrequently. So one can look for structures which occur infrequently, which are roughly opposite to what is called best substructures. Best substructures are those substructures that occur frequently and thus can compress the graph. And then there is this minimum description in principle that trades off between compression quality and size of such substructures. But maybe like we can skip this because we don't want to discuss MDA. Yeah. So the high level idea, at least the high level idea, if you are not going into the details for like structure based approach in the static attributed graphs is like, so first is the problem of finding unusual substructures. For this, like minimum description in principle can help us. And then the problem of identifying unusual subgraphs that contain non-unique attributes is like maybe one can define some measures that penalize the subgraphs containing a few common substructures, which makes them more anomalous. Yeah. And then after these, like so, after this high level idea of what are these structure-based approaches, we can move on to these community-based approaches for the static attributed graphs. But note that, like, as I said, like, we won't be discussing too much about the static attributed graphs because these are a bit trickier to handle. So, usually in community-based approaches, like we were trying to find out bridges previously, but note that now we also need to consider these attributes, take these attributes into account. So, one needs to identify those nodes in the graphs, uh, the attribute values of which deviate significantly from other members of the specific communities they belong to. Suppose you have detected some communities, and then, like, let's say there are some nodes whose attributes differ significantly from other nodes of the same community, then probably that node is a anomaly or some outlier. Yeah. And these can be thought of as being community outliers. So for example, like a smoker in a community of vastly non-smoker baseball players is an example of a community outlier. And there are some algorithms which we going not go into, but like there's an algorithm which is CODA, which is a unified probabilistic model that simultaneously finds community as well as spot community outliers. And then there's this code triangle uh, models like complex anomalies could be revealed on only a subset of relevant attributes and which are more apparent in high dimensional feature spaces due to the loss of dimensionality. So yeah. Okay. But one thing which has like gained prominence obviously with like advances in machine learning is like trying to learn these relations, like so there's this problem of like these attributes and everything in these uh, outlier this anomaly detection in like static attribute graphs. So what one can try to do is maybe okay, so we have these machine learning models and everything. So what we can try to do is like learn relations between different objects in the data given to us, like between the relation between edges and nodes. So we can try to model some kind of mathematical relation and try to learn those relations. And if some node does not follow like relations like the other nodes do, then probably there is some anomaly going on. Or like some relations are very different from other relations, then there is some kind of anomaly going on. So this is a very high level idea. So, but yeah, like we try to exploit the relationship between the objects to assign them into classes, anomalous and normal. And this is different from proximity-based approaches, which aim to quantify like autocorrelation among graph objects. So in proximity-based approaches, we are trying to quantify all of these things ourselves. Where, as in these relations learning, we are trying to learn these relations. And these algorithms are often more complex and can model and exploit more complex correlations. So, like proximity-based approaches, for example, are like very naive approaches which can model like simple models of proximity, like maybe distance or like connectivity and so on. But with this relation learning model, you can model some more complex phenomena. So usually the methods of relation learning exploit one or more of the following inputs: the class label of the neighbors, the node attributes, the attributes of the node's neighbors, and so on. And then there are many models in relation learning. So, like some are local models, which look at local properties, and some are global models, which look at global properties. So, for example, like there are like so this again, these are not exhaustive lists, but like some lists have like local models. So one model proposed, one knife-based model proposed by Chakraborty in 2007. Then one proposed by Neville and Jensen in 2000. Again, a knife-based model which uses like iterative classification algorithm for inference. So all of these, like none of these have been discussed in the lectures, but if you want, like you can just uh, search for these authors and the year and the relevant research paper will show up, and you can read up these research papers on your own if you are curious about these, what goes on with these models. Similarly, there are like the local model by Goen Couture in 2003, similarly Gallagher et al. In 2008. And then there are global models like one by Friedman et al. In 1999, Tusker et al. In 2002, and Michelson was in 2003. And you'll see that at least these models, so note that these are like all are like pre 2010 models. And you can see like all of these are, none of these are using like these neural nets or anything, because neural nets and everything gained prominence after 2010. Before that, all a large part of the community actively worked using these Bayesian models and like probabilities and all. So all of these models are based on like probabilities. So they are like very highly mathematical in nature. But like if you look into like recent literature on these relation learning, if you just look up like maybe the recent papers in relation learning, you'll see like quite a lot of new papers in this area uh, try to use these neural nets and yeah, the recent advances in deep learning and all. So yeah, so there are like multiple layers with like we had like so community has moved on from using these probabilistic models, although these also serve us well, but now have moved on to these neural nets based or machine learning based models. Yeah. Okay, then so if we know what's going on here, then let's move on to this anomaly detection in dynamic graph. So right now we just discussed till now the whole discussion which we have done uh, is just about the static graphs, and uh, like we already said that yeah. So the all the discussion which we had done till now is about like anomaly detection in static graphs, like the graph is not changing over time. So this was the problem. The given thing was a snapshot of a graph, and it does not change over time. And then the graph can be plain or attributed, and then we have the structure-based approaches or like feature-based approaches or distribution learning and so on. But what if the graph itself, which we want to take the anomaly, is not a static graph but a dynamic graph? And what does a dynamic graph mean? The graph itself is changing over time. So it's not like you have a very concrete thing to compare against. Like it's like the graph is again like the graph keeps changing over time. So the anomalies, the associated anomalies can also, or associated anomalous substructures can also keep changing over time. So then keeping track of these substructures and identifying like which of this is anomalous and which of this is non-anomalous is like a really, really tricky thing. Like, I hope you can imagine the complexity. Like already we were struggling with, we went from like plain to attributed graphs, and now we are adding this another dimension of like the graph changing over time. So these anomalies are also changing over time, and like yeah, so this becomes like really tricky for us. And yeah, so for doing these kinds of like for anomaly detection in dynamic graphs, so yeah, so maybe like first we define the problem like a bit more formally, although I just described it to you guys right now. But suppose you want to detect events in time series of graph data. So what is dynamic graph anomaly detection? So suppose we are given a sequence of plain or attributed graphs, then we have to find the timestamps that correspond to a change or event, as well as let's say the top k nodes, edges, or parts of the graph that contribute most to the change. So so basically what we want to see is okay, maybe some changes have been done in the graph, and what was the most contributing factor to that change, and maybe like so there must be some underlying factors in the graph because of which the graph has changed over time, right? And we want to identify those underlying factors because of which the graph has changed the most, and because these factors are somewhat anomalies because these are the factors which are responsible for the graph changing over time the most. Like if there were no anomalies, then maybe like graph would have remained the same. But since there are some maybe some anomalies, like the most prominent anomalies or the most prominent events contribute to the graph changing over time the most. So yeah. So most usual desired properties are scalability, sensitive to structural and contextual changes, and importance of change awareness. So basically, the solution which we find, like maybe the algorithm which detects anomaly in dynamic graphs. The algorithm should have these kinds of properties. It should be scalable, means like however large you make the input, the algorithm should still follow. It should not be like the algorithm was too slow to implement at the point. And then it should be sensitive to structural and contextual changes in the graph. Like if we change the underlying graph itself, then the algorithm, so basically the algorithm should not be hard coded with respect to some certain graph structures. Like if we change the underlying graph, then the algorithm should still work. And then it should have this importance of change awareness, which is like something which I already described. That the algorithm, even if we change the graph, still the algorithm should be able to give us good answers. Yeah. So there are like so again like we won't go into too much details on like how do we do anomaly detection in these dynamic graphs, but on a very very high level, like what kind of approaches are usually there for in this domain. So the intuition is usually that similar graphs probably share certain properties, like so this is similar to like what we had these feature based approaches, like where we said that okay, like uh, certain features may be common across the graph and may be different for anomalies. So similarly here in dynamic graphs, the intuition is that similar graphs probably share certain properties such as degree distribution, diameters, eigenvalues, or maybe some other properties. Note that this is not an exhaustive list of properties. So then a very general approach, like not a specific approach, but a very general high level idea would be to extract a good summary from each snapshot of the graph. And by summary, what do we mean? Maybe like as the summary can be this degree distribution, the diameter, the eigenvalues, and so on. And then we can compare consecutive graphs using some distance function. So after having this summary, maybe like if you have a degree distribution, then the distance function can be KL divergence or something. If you know KL divergence, it's well and good, but it's really not important right now. I'm just giving an example. So first you take some snapshot. Uh, so from each snapshot of the input graph, you take a good summary, and then you compare these summaries over time. Like you have associate some kind of distance function to these summaries and see like how much are these summaries changing over time. And when the distance is greater than some threshold, we can characterize the corresponding snapshot as n plus. So we can say that the timestamp that corresponds to change or event will be when this summary changes the most. So basically, in these dynamic graph, what we want to find out is the anomaly is not in terms of like specifically just not in terms of like some substructures in the graph, but also in the terms of like okay, like there can be at some point like maybe some event occurred and the underlying graph has completely changed, and we want to detect that. Like maybe at day 13 the graph till day 13 the graph change was following some certain pattern, but on day 14 it suddenly changed, the pattern suddenly changed. So maybe some big thing happened between days 13 and 14 because of which the pattern changed, and we want to identify this change as we already said. And then we also want to identify like what were the features like the top nodes or parts which contributed to this change the most. Yeah. So yeah. So the general idea then would be okay, like so you want to first you want to quantify this change, and this quantification can be done by this summary and then a distance function of the summary. And then when this change is too large, when it's larger than some threshold, then we can characterize the snapshot as n plus. And so like if this is a very high level framework, then still like you can see like although this is a high level idea, like there are many variables in this. Like the so novelty of an algorithm lies if it follows this framework in the graph summary function which it constructs, the distance function it uses, the way it defines and chooses the threshold. So all of these things will be specific to each algorithm which we are implementing. And yeah, the algorithm, the better the wiser the choices for these three things, the better will be the performance of the algorithm. So for example, like so there are some common approaches or like uh, some like so the functions which people use for these like graph summary and distance functions and these thresholds are like these are very common choices, although this is again not an exhaustive list, but some things which people use. So for example, people use this maximum common subgraph distance of the adjacency or two hop matrices. And another thing which people use is error correcting graph matching distance, which is number of edit operations needed to convert a graph to another. And then so you can look into like these definitions in detail on the internet. Like these are very common definitions and you can find these yourself. um, but yeah, on a high level I think the definitions are clear here also. And then there's this graph edit distance which people look at, which is simplification of like error correcting graph matching distance, where only topological changes are allowed and no changes in edge weights are allowed. Similarly, Hamming distance for adjacency matrices counts the number of different entries in the matrices. Then there are variations of edge weight distances. For example, lambda distance of the adjacency 2-hop or Laplacian matrix is defined as differences in the whole graph spectra or top k eigenvalues of the respective matrices. So maybe if not, you just don't look at the whole adjacency matrix, but maybe look at eigenvalues of the matrix, or maybe like top k eigenvalues and see the if how much have these eigenvalues changed. Then there is this diameter distance, which is like difference in graph diameter defined as the greatest of the longest shortest path for all. I think we have already discussed in one of the previous lectures what a diameter is. So the notion of the summary being the graph diameter is like, makes natural sense. So, yeah. So so these are like some high level like some approaches which are generally used, but note that again, this is not an exhaustive list. And one example of like an approach used by Akoglu and followed those in 2010 to detect anomalous nodes in a graph sequence was this approach where the intuition is a node is anomalous at some time anomalous at some time frame if its behavior deviates from its normal behavior. And so these are like very high level down. What do you mean by behavior and what do we mean by normal behavior? And so the questions to answer are at what points in time many of the nodes in a given time varying change their behavior significantly and can we characterize which nodes change behavior the most. And so for this, what Akoglu and follows did, they summarize each node by a set of features extracted from its EgoNet. So again, it's an EgoNet based approach. So, so again, it's a local approach because it just utilizes EgoNet. And EgoNet is very local to every. So 12 features are considered for every node: in degree, outweight, number of neighbors, number of reciprocal neighbors, number of triangles, average in weight, average outweight, maximum in weight, maximum outweight, maximum ratio on reciprocated edges in the EgoNet. So this is not GoNet, but EgoNet, I think. So, yeah. And then using this summary, you try to formalize some kind of a distance function and see like what things change the most. So yeah. So again, like as you can see, like this is not so this is not something which is very automatic or this is a very subjective choice, like what features to include, what features not to include. This is not a very rigorous mathematical argument that these features will always be optimal. But one can do is maybe apply some intuitions to see like which features to select to, and then test it on like some data sets, see like which features gives the best performance for us. So something like that. Then, other than these kinds of structural approaches, there are some decomposition based methods for like anomaly detection in dynamic graphs. So, for example, the one of the examples is like yeah, method first extract the principal eigenvector from the adjacency matrix, which is also called activity vector. Then, by applying singular SVD singular value decomposition, which I hope everyone knows about. So, by applying singular value decomposition on the matrix, uh, this typical activity vector is found. And this is usually done in vectors in a time window of W. Like you look at like let's say the past W vectors. Uh, you try to find out these activity vectors and difference between current and typical activity. So you find these typical activity vectors using the SVD on like some time plus W uh, time frame, and then the similarity between current and typical activity vectors is computed as cosine of the angles between them. And yeah, so this is the distance function which we are referring to between the vectors, and the summary which we are referring to is this activity vector and this typical activity vector. There are two notions defined at every time frame in this at least in this one of the decomposition methods is you try to find out the eigenvector of that adjacency matrix and maybe like some past and this is some summary of some past W eigenvectors and then you try to compute the distance between them because as Okoglu and Polostas also did in their approach, what they did is a node is anomalous at some time frame, its behavior deviates from its past normal behavior. So what you try to do is you try to see this eigenvector and how much it deviates from the past W eigenvectors. And this deviation is not usually in terms of like distances because like in vectors the magnitude of vectors can change, but like you try to usually compare distance between vectors by the angle between them. Larger the angle, maybe you can say larger the deviation between vectors, and this angle can be measured using cosine. So yeah, and then there are some community based methods here also, uh, which monitor graph communities or clusters over time and report an event when there is structural or contextual change in any of them. So you can maintain communities or clusters at every point of time, and whenever some community changes, then you can try to quantify like how much does the community change, and maybe you can have some kind of distance function and say, okay, like if the communities have changed by a drastic amount, then something has occurred, and that is like anomalous time set. So it looks at changes into subsequent snapshots or all snapshots and text communities and outliers simultaneously. So I hope we did not discuss things in too much detail at least, but I hope you guys got the high level idea of like the general approaches which we try to implement for anomaly detection. We discussed some approaches like this oddball approach we discussed, but other than this, all of everything else was done on a very high level. If you want to go into more depth, you're welcome to read up all of these references which have been mentioned in the lecture as well and in these notes as well. Yeah. Okay. So that was it at least for the summary part. So then now uh, uh, I have a bunch of questions prepared. So I would have loved actually to for some people to actually be present in the session because then it would have been more fun because I would have asked you guys to answer these questions because now if there are no if there is no one in session then this question answers become a bit monotonous and especially when most of the questions are pretty simple and just um, are based on what we just discussed. So yeah, but nonetheless, we can get started. So first problem is outlier detection is different from network-based anomaly detection. So is this statement true or false? So yeah, so actually this statement is true, as we already discussed that outlier detection. So this is true as discussed in the lectures. And why is this true? As we already said that like we already described that there's some difference, underlying difference between outlier detection and anomaly detection. That outliers are usually singular points, whereas anomalies are like some patterns which are different. So anomalies are much broader terms than just outliers. So, yeah. Second question says which of the following are node level features. So again, this is present in the slides as well, and I think you don't even need to look at the slides, but maybe just looking at the slides, we already described what are node level features. So, eigenvector, closeness, betweenness, local clustering coefficient, degree assortivity. These are node level features. So this is again not an exhaustive list, but yeah. So eigenvector, betweenness, degree assortivity. So these three are definitely node level, which we already discussed in the slides also. And note that modularity is definitely not a node level feature. So just ACD is the correct answer. So options A, C, D are correct. As discussed in the lectures. Yeah. Maybe I just underline so that it's easier for you guys to see. Okay, and then third question. Okay, so this is a bit of an interesting question. So consider that in an SNA class, so all the students, so SNA is social network analysis here, it's not anything technical. All the students talk to the instructor more than they talk amongst themselves. What kind of anomaly can arise that can help us detect the instructor using the oddball algorithm? So note that uh, if all the students are talking to the instructor more than they talk amongst themselves, then if you want to take the instructor, so what's actually happening is so the edges between among the students will be very less, but the edges between students and the instructors will be a lot. So if you think of the instructor as an ego node, then all of these students will lie in the ego network. But note that this ego network will be more like a clique, because not a clique but a star, sorry. It will be like a star because students don't have much edges between them. but the edges, there are a lot of edges between students and the ego node. So that's why this will be a near star. So option B is correct from the definition of near stars. So this is just the definition of near stars, that if you have a lot of uh, edges from between ego node and if the degree of ego node is high, but all the nodes uh, other than the ego node have very few edges between them. So that is a near star. Similarly, so in fourth question, consider as another SNA class where students talk to each other and to the instructor as well. So what kind of anomaly can arise to help us detect the network? So what kind of anomaly can arise here, which can help us detect the network? So here note that students are talking with amongst themselves also and with the instructor also. So then with respect to the ego network of the instructor, so there will be a lot of edges between every pair. So there's a high chance that there will be a lot of edges between any two pair of nodes. So there's a high chance that between any two pair of nodes, there will be an edge between them. So this will be more like a near clique, because almost like edges are present between almost all pairs of nodes. So that's why this is a near clique, which is like, again, we are from the definition. So option A is correct from the definition of near cliques. Yeah. So I hope this makes sense, and then maybe we can go on to the next question. Yeah. So this is Jen. Then so the fifth question, that in a dynamic network, what can change with time t? Only nodes, edges, both nodes and edges, everything remains constant. So note that, like as we said, like in a dynamic network, the network can change over time. So node can change as well as edges can change. So both nodes and edges is the correct answer. So yeah. So option C is correct, as discussed in the lectures. So okay. So sixth question is, Reliance, which previously concentrated on petrochemical industry, suddenly introduced geo. None of its traditional competitors had taken such a step. What kind of anomaly detection method could be employed to identify this situation? So note that. Note that. So Reliance and its competitors, Reliance and its like petrochemical competitors, all of them were part of a community, right? The community was the petrochemical industries community, and suddenly Reliance have jumped into this telecommunication industry as well. So they have jumped ship from one community into another community. So actually, Reliance now are part of multiple communities. Previously, they were part of this petrochemical industries community. So actually, like there's a change in communities of this Reliance, and hence these kinds of community-based methods can help us identify the situation. Like I hope this kind of makes sense, because structure-based and feature-based, maybe like if you define appropriate structures or features, this can be done. But on a very high level, at least, if you have to pick the best option, if you have to just pick one option, then the best option, which is straightforward from here, is the community. Because previously, all of these petrochemical industries were in the same community, but then Reliance went on and went into this telecommunication industry also. So option C is correct. Maybe person should have the question. So since Reliance was previously part of the community of petrochemical industries, but has now ventured into the part of telecommunication, community of telecommunication industries. Hence, community-based anomaly detection can help to identify this situation, and hence option C is correct. Yeah. So I hope this makes sense. So yeah, then we can move on to the second question. So which is the last question for the day. So in window-based method, what number of elements skip between the starting point and of two consecutive windows is called? Okay. So I think I did not cover this in the summaries which I discussed. But nonetheless, like anyways, like I always say, you are expected to watch the lectures before watching these sessions because I can't cover everything in like which has been discussed over a week in just like 2 hours. So yeah. So actually, like this has been the lecture. So there, these window-based methods and the element skip between starting point of two consecutive windows is called hop length. So yeah, so the answer is option A. As discussed. Choose. Yeah. So, so okay then. So we discussed these 7 questions today. So I guess like this was it for the day, like the questions which I had for the day. So we discussed these 7 questions and like summary of whatever was discussed in week 9. So the yeah. So the week 8, like we did not have any session for week 8. So probably like we'll inform you guys if if we have any makeup session for that. So other than that, like yeah. Hopefully I'll see you guys in person in the next session. So same timings like Monday 6 to 8 p.m. next week, and we'll discuss like the week 10's problems. So okay then. So till then, like thanks a lot for watching the session, guys. So uh, till then, goodbye, guys. Again, thanks a lot for watching.